right? The standard deviations, estimate, best estimator. So, and earlier we say that, okay, for the case of we have one guy, and we have 20 sample n equal to 2, and we can estimate the sigma from this equation here, right? So now we have 3 guys doing the sample. So that means we have more sample groups already, right? So naturally, why don't you make use of this same thing? Measure that, right? So for repeatability, we apply the same technique as we learned earlier, right? So between this operator 1, operator 2, operator 3 there, and each of them, right, 2 units, those are things there. So we have sample size is equal to n equal to 2, right? Number of trials, right? Sometimes in this AIAG, this case study, sometimes you do 2 trials or 3 trials, right? Kiasu a little bit, the same part you read it 3 times, but 3 times a bit quite involved. But maybe it's a little bit more data, right? More solid. But so typically it's either trial 2 times or 3 times, right? So in our example, it said 2 times, right? So the number of trials here, see, we have is n equal to 2, right? Sometimes people we have 3, right? So but in this case here we have only 2, right? And we have many subgroup sample, right? So 20 each, so we have 60 subgroups. So we get a solid sigma, we can get this thing here. And question is that how we're going to get it later on, right? So this one should be simple. We have R being operator 1, operator 2, operator 3, 1. So you take the average of it, so you can get the grain of this one, right? Alpha R, then we can get it. So we can get the repeatability. Then how are we going to get the reproducibility? The reproducibility, the guy said that since we are using X bar, things that, and we will try to look at it, how is the best way you can make use of the data. So if you look at it in this form, right? In this form here, right? Operator 2, operator 3 here. And you get all the readings, right? The average reading, this thing here, the average reading from here, average reading from here. So you see that every operator, when you measure it, right, and that his behavior is this way. X bar R chart, second one, third one, right? So it looks at a block chart like that. This is, you know what it means, right? This is the mean, this is the first quarter, second medium, this is the third quarter, right? So you have the variations on the readings you have. And say the guy there said, okay, so we want to find out the variations due to that operator. And this guy as a group, we have a mean value, this guy has a group a mean value, this guy has a group mean value there. And how is the best we can do it? So they make use of the same thing there, see, it's like our case here, right? In this case here. But then in this case here, see, we got slightly restricted things there. See, we have only one group of 3 operators. So you still try to insist you're using this thing here. Somehow a mystery guy over some number there, right? So the way it could be is that we have only one group, but the subgroup size is number of operators. So this is 3. So they try to make use of this arrangement, X bar R chart, to make use of this type of equations to get it. But it's a bit forceful in the sense that this guy's using one subgroup. Right? But then, see, if he uses this approach there, somehow we'll find this thing and this thing what is appropriate for n equal to 1, right? So in this case here, see, you also see that we have each guy, we have a distribution, something like this one here, right? And when you consider this out data, actually this guy, when you read the readings there, see, This reading here also compounded some of the repeatability reading inside here. So when you get this number here, see, this number is very close. And because this repeatability, right, is embedded inside here, and somehow we have to normalize it such that one group we normalize it, and then to take out the reading there. So we'll come back to that later on, right? And then on part to part, if you take, right, the readings of 20 parts, and each part, right, the average reading is this one here, right, and you get this reading here, right, this plot here, right. So you look at it, you get 3 plot here, 3 point here, 3 point here, the mean here, right. So we have one group of this part spread over 20 parts, but we have a mean reading there. So we can make use of this similar approach there, right? For one group of parts, group size, number of parts, right? So bear in mind with this one, right? And this is why this guy is very smart, logicians. I say, if I bring the same principle there, why do I go with this things there? But then only nutshell, my problem is that if I use this, my subgroup size is small, so there will be some theoretical study of tolerance or of the variance of that, right? So this guy, see, A.J. Duncan, this guy, he published Quality Control Industrial Statistics. This is a very quick guy, in 1956. And then 76, he had a few iterations here. 76 is one great book, and then the latest one is 86, if I remember, read four editions. Inside here, this guy studied a lot of things. And then he used all the numerical theory, right, subsequently, and then he defined the D2, right, into a table, calculate it. If this is a subgroup size, this is our normal N, but then in his table there, he used the letter called M. M, that means the sample size, subgroup size, M. So it's a normal, our N. And then if you have number of subgroup, G, that means the number of sample, right? So in this case here, see, he calculated the theoretical value, right? If you have this distortion, if it's only one group or two group, and then with this different number there, right, you can get a different estimations of D2. Right? So you have this number here, and that, so the way to read is that this is all the columns there, matrix there is all the D2 number. You give it up to 5 digits, more accurate than the one that we have in this book here, right? Here, right? Here is only about 3 digits, 4 digits, 4 digits. Some numbers are 3 digits, right? D2 also. D2 is 3 digits only. This guy give you up to 5 digits. Minitab make use of this table. When you calculate it, Minitab give the table that gives the value instead of the value we have here, right? Minitab is more decimal points, right? Make use of this table by A.J. Duncan on that. So our D2 is actually, right, here, they give you the D2 is an infinite number of subgroup. That means the number of sample, right? The number of subgroup is very big. Bigger than this guy here. Actually, he has a table up to 20. I didn't put it inside here because the number will be ridiculous. If you use it in an exam, you cannot see the number of it. So I didn't need it. But if you go to this here, I switch it over. If you use the latest AIAG, AIAG, the group earlier, I see that you can go into the internet and search it. The sample that I have, one of them earlier version was when I talked to the fourth guy there, I got a copy from them. But the electronic one. So you go to the internet, you can search it. So, and this is the 2010, the fourth revision AIAG number. It's just the body only. This guy here is subgroup, Philippine transposition. So this guy here is a subgroup size, it's M. Our subgroup sample size normally we say control charge N. This guy is number here, right? So you have all the way to 20, all the way to 20 to quit there. So, but anyway, this table here, up to 16, right? But Minitab has the details inside there. When you use it, you see this is number to calculate, right? Anyway, so don't worry. Okay. Right. So this is a table that when you calculate subgroup size only, the group number, right? Subgroup number of subgroup is only one, not the subgroup size. Size can be just like we say here, right? So we have only one group, but the size is different, right? 3 appraisal, number of part there. So in this case here, right? So we have only one group, so we are looking at this table here. Only one group. So he has this number for us to do the computation, right? So if you have that, right, then it's very simple. If you refer to this that we have now here, right? So first, repeatability. The repeatability, sigma is this guy over D2. Our D2, because now we have 60 sample, right? 60 sample. Operator 1, 20 sample. Operator 2, 20 sample. Operator 3, 20 sample. So it's 60 sample, right? So the number is very big. So we use D2, right? And that, so there's no problems, right? So we can use this number, right? The trial is only 2, right? Subgroup size is, look at it here, right? Number of group, right? The size is number of trial. Many groups, so we use D2 here, right? And then estimated reproducibility, we also like to use this equation. Now, this one, you see, this R double bar, right? It's basically, if you look at that, is that we already have R bar for this guy here, R bar for this guy here, R bar for this guy here. So you can get the average of this one to get the R double bar, right? So this is what we have, right? Okay, so it's quite easy. Now the reproducibility. So we can make use of this equation. Now because you have only one sample, right? So I tabulated it here, right? So where is this double? This range here? This range is this guy here. So in this case, what is this? Right, we have this number here, 22.30, 22.05, 22.06 there, right? So we can make use, we can get the max of that minus the minimum of that, we can get this range of the mean of each one. And then this number here, we can read it from there, right? In this case here, what it is? Our number is one group, subgroup size is n equal to number of appraiser, right? So the appraiser, number of appraiser is 3. So we can get this, right, to read it here, right? But then, as you said earlier, when we look at this part here, because we got these distributions within here, so we got some repeatability element. So we must subtract it out. So you normalize it, the repeatability, you get it from here, square it, and then you normalize it, number of parts divided by number of trials, right? So this term we got it is inside here. So since only variance can add and subtract, right? So this variance, gross variance that we have, subtract the contributions of repeatedly compounded inside because of this thing here, right? So we can get the reproducibility, right? Sometimes in this equation, if you get this number is greater than this, then what we do is that we set this, the whole thing here, right, is equal to reproducibility is 0. Because you cannot have negative square root, right? And why we have negative? Because in this, our example here, we don't take into one factor of consideration the interaction between the operator and the parts. So sometimes, right, when this operator, because this part is so smooth, my finger is not so big, right? Like more, you know on that, see? When you want to handle small part, they were very clumsy, right? And then the other guy there, he happened to be an Asian. So small, he can handle that. So when you do it, you get the problems of interaction between the parts, right? So that part there, see, you know, if you want to do ANOVA method, ANOVA calculate inside there. But if you use the X bar chart there, there's the computations a bit more complicated, so we don't do it. So that's why sometimes if you see negative, you set it to 0 because we need to consider the part, right? Okay. Then on the part to part, now this is the section we deal with, right? We have only one subgroup because we have only 20 sample, and then we have readings. For example, the sample size number of parts. So in this case here, right, we got this. This is equal to this max minus minimum, right? And D2, 20 parts. We have only one group, so we use a D2 parts asterisk. Right? So you look at that, this is a number, then you can plug in. Right? So this is quite mechanical. Once you understand that, because the guy want to use it, X bar R chart there, see? The method using this equation, right? Generic equation to get the standard deviation, right? The estimator, we should use it as estimator to estimate this guy here. See? So this is what the various things will come up to be, right? And that's all right. So let's quite look at it. You have this equation, this part here, and then because this one we have a lot of subgroup, so we can use D2. This one is only have subgroup only one, so we use this Duncan's table to do it, right? And in the Montgomery book, if you read it, he will use this one. He tried to say that yes, it is almost the same there, to use it. But if you want to use the plain AIAG method, AIAG use the A.G. Duncan the table there. And Minitab use the A.G. Duncan there. So we stick to this one, right? And if, for instance, if a subgroup number is less than 20 or something like that, right? It's 16 in the table we have, right? We can also use this D2 asterisk here if you want to. It's more accurate. But, I mean, for our purpose, we can use D2 group size big enough, right? Okay? So, if you look at that, you have this table. It's very useful. As I showed you earlier, in the year 2010, the Red 4 of AIAG, they have 20 by 20, they expand this one up to 20, right? And then after that, they say anything beyond that is D2. So doesn't matter, okay? So if we have that, right? So we can go to calculate, right? All the part equations are all there, very mechanical, right? So we know that total is equal to product, this guy here. This guy is break into two parts, right? Reproducibility and this thing here. And that repeatability, we know this can get here. And then this is where the estimated is this guy here. And then the reproducibility, actual one, is you have to take care of this part here. Minus out, you get this. And then the part to part is this equation. So you apply this thing inside here, you got it. The equation, very simple. Right? So you look at that, I'll just go inside there, right? It's just, I go back, this is for you to cross-reference here, right? Okay. So we have this. All right, divide by 3. So these are the number, 1, 1.5, 1.2, right? So divide it, right? Okay. And then you check the R chart, D3, what is it? This is n equal to 2, right? So you check it out and then multiply by this number. So upper control limit is this one, lower control limit is. So 4.03, check through 4.03. Anyone 4? No, right? Look at this one here. And the second one, range, also no. This one, so this is no out of control in the R chart, right? So good, we are good, right? So then we are good, then we go to calculate the repeatability, right? This guy is, right? If we use this number, right? So this is using the, if you use 3 more digits here, 2 more, this is using the Montgomery 1.3 number, but then you can use up to 5 number, then you get more accurate. Okay? So now, reproducibility, 3 appraiser, there's only 1 subgroup here, right? So you have to use D2 asterisk this guy here, right? So there are 3 values. These are the 3 values we have. This guy, right? This one, and this one here. So you can get the max and min, 22.6 minus this guy here, get this one. Right? Since the subgroup there are 3 appraiser, n equal to 3, right? So n equal to 3, you look back. Right? Or you look back to this table here. I clean it up, let me clean it up, right? Right, we have only 1 subgroup, right? We have 3, so in this table here. So I just plug it into here, okay? So you have it 161, so you get it estimated reproducibility using this equation. You get this one. And now, see the repeatability is this one here, right? This one. So you have to square it, and divided by the number of parts and number of trials. How many parts we have? 20, right? The trials we have? 2, right? So you normalize it to per unit, so then you get it, minus out, and then square root of it. Okay, this reproducibility. So once you have reproducibility, our R and R square is equal to this repeat square plus repeat, like the right, reproduce square, right? Correct? We have this one, is very easy, right? You can get the measurement system derivation, right? Okay? Now, the parts. We have 1 group, but then we have 20 parts, right? So the RP is this one, right? That's what you said earlier. So this is the bottom here, right? Okay? So, and then we read out the D2. So you go back to this part here, right? Okay? So you just divide it, you get this part. So total is this one this one sum together, and then square root of this one, you get this. Right? Very mechanical. Once you know the equations, you just like that's what you like, right? And then once you have it, you can calculate. If you use 5 or 6, you must specify that k equal to 5 or 5.15 or 6. Huh? So in this case, you use 5.15, and that R and R is one here, right? So, and the spec is 60 minus 5, 55, so you get 0.1 here. This one, right? If it's 6, they're about slightly, not much different from there. Right? And then from GR and R, right? This one over total, right? Total is this guy here, right? This one here. Remember? So this one here is 3.4. So PT is equal to 0.10, around there, huh? Then GRR, percentage, you use percentage, then you multiply by that, so it's just fraction, 0.3467, right, this one. So what is the conclusion drawn? So, based on the step, 10 truncated, 0.1, just barely, just acceptable, right? If you want to use it to measure your process, with respect to the product specifications or tolerance, right? You have 10 divisions there, you're okay, right? And you want to use it to measure process variations, 24% of the error. Can you use it for process control? Can you use it for process control? No good, right? No good. So in this case here, see, you have to look at it. When you look at the thing there, what is your intended applications? If you intend it for applications for process control, you have not enough discriminations. Tell it you want to use it for control chart, right? As I said, we don't have probably enough resolution for that. But you just want to screen out and say, finally, see, at the end there, audit there, right? Give it to customer, right? Customer needs to spec there. Then probably, okay, this is good enough. Right? Now, then, right, before I go to here, right, let me touch base on this one here. So, related to here, you remember this chart in our capability study? Right? If you are somebody, the spec has to be very much wider than the processor, or else you'll get fired already. You're not doing your job, because the process is, you know the CPK, right? So your tolerance has to be very much bigger than the plus minus 6 sigma of this guy here, right? This is 6 sigma here, right? Plus minus 3, right? Plus, let's say plus minus 3 sigma there, right? So equal to the spread here, right? And then a control chart there, see, this is a plot of X bar, right? This guy is very much smaller because of central limit theorem, right? So this relation, this is the thing here, right? Correct? Right. So if you want to use a process control, see, based on our gauge there, see, tolerance-wise it's okay, but then process control, hey, it's no good. For the whole plus minus, the range here, right, we have, right? And it is going to be not enough resolution for us, right? So coming back, if you want to take sample, right, for the MSA, so from random from process, right, you take sample, what you get is this guy, right? And people will say, oh, okay, so we'll have this range, right? But you say that, okay, sometimes people say, okay, since I'm going to measure from the range, right? Let's say our case here, we want to measure it such that we take the tolerance as extreme, right? So I take sample, spread it from the minimum to the maximum tolerance, right? So if you take sample from minimum to the whole tolerance there, right? Let's say that our sigma, see, would be like that. So if this is what we have from the range there, this in this case here, like this case here, upper spec limit minus lower spec limit is our range, right? You take something sample with that spread, the big spread there, like this one, right? So in this case here, this guy will be very much bigger than this, right? This guy also very much bigger than this. Am I right to say that? Right? Okay, so if there's a case there, right? This is what we say, right? Okay, now, we have this scenario. Sigma total equal to product square plus this measurement system. This R and R, this repeatability and this square on that, right? Our gauge definition, this guy here, right? So, if you take sample from the full tolerance or the full product range, this thing here, right? What will happen to this guy here? Assuming your equipment is good, it's fixed, this part is fixed. If you take sample from a full product range here, you are going to measure something like this one, right? Right? So this case here, come to here, right? So this value, based on this sample, will be big, right? So if it's big, this is the same, this is big. What happened to this value? Small, right? So if you use this guy here, your GI and R will be small, right? So if you use this guy here, this case here, right? What happened? This guy is constant. This guy will be smaller than this guy, right? Based on this relationship we have here. Okay, this one, right? So what happened to this equation here? The GR will be bigger, right? If this guy is small, this guy is based on this one here, your sigma total, right? Smaller. This guy is sigma total is bigger, right? Okay, right? So you see that when you take your sample based on tolerant range or the natural process range there, see, it's going to influence this value, right? So when you want to, if this guy, right, is small, if you measure the tolerance one, right? So what does it say? Given a scenario that you may have a marginal case, right? You say the gauge is good, right? Small value is good, right? Small value is closer to good, right? You have big value is closer to bad, right? Am I right? So then you see that the way you select your sample for your gauge R and R study is going to influence your perceptions of your final value coming out of there. So it depends on your perceptions. What is the right thing to do? If the gauge is bad, you want it bad. If the gauge is good, you want to call it good. But then you don't want to use a sample to confuse people and saying that, okay, I use a full tolerance sample there, see, to get my sigma, and thereby my product there, see, flated it out, subsequently make the GR now look small. Then say, hey, I may be manipulate a little bit purposely. My gauge is not so good, want to make it so that my GR looks so small, right? Closer to 0.1 or less than 0.1. Instead it's 0.151, maybe it's become 0.1 already. Then you are not doing yourself a good service, right? Am I right to say that? So that's why, you see, then I say this one, right? We go back. Right? when you select a sample part, that's actually represent what is expected from natural process variation. And you take random sample part per day over several days, or it may take one or two over morning and then afternoon, something like that. So you do some natural process variation, spread a little bit on that. You don't purposely go to select that, okay, I get a minimum value, maximum value, so I select the minimum value, maximum value, and some value in between there, and subsequently I go to artificially inflate or deflate the GI and R value. Right? And considering the fact that if we are knowing this relationship here, right? So you want to get parts represented here instead of representing this part here to influence your value. Got it? Right? So this is a lot of, when for practitioner, right? This is a subtle point. How to get your sample to do GI and R study. This is quite earlier, there's a lot of people earlier, but then you think about what is the right thing to do. Okay? Then you go back to what we said earlier. Right? This part here, right? The number looks good on the tolerance, for the customer tolerance on that. But then the number doesn't look good on the process. So in actual case, you want to control the process, which is more important. Or some people say, hey, meeting the customer requirements, okay, good enough. But then you see, if you are a process guy, you want to know what your process standard deviations or process variation contribute to you, right? So you want the equipment that can discern what is your process variation. Subsequently, you can go to do your CP, CPK, or those are standard deviation reduction. So in the world of you want to drive or Six Sigma, those are things. What you actually want to do is that GI, not PT ratio. Right? So that's why your, where is this thing here now? Okay, did I close it up? Oh, okay. Okay, so if I get back, where it was? How do I get back? See 100 old pages. The measurement. Right. This is the soft copy of that. Okay. So you look at that, and they say there, right? Actually, the focus is on the GI and R. Anyway, you all go to look at it, for those who practice that, you can see that. Its focus is GI and R, see? Okay? Right? So that's how this thing is done, right? And then, for those guys, they want to use a Minitab, right? And Minitab, I have this example shown here. Okay? So Minitab want it to be inside column, that kind of stuff there. See? So the part, you have to go 20 parts, this guy here, the appraiser number 1, and then first measurement, second measurement, that kind of things there, and then subsequently get the measurement. They want to arrange those data into column. So if you look at that, what they need to do is a quality tool, case study, right, and cross. So you get the part number, you got this appraisal number and measurements there, right? And we want to use this X bar R chart there, and options. You want to do the PT ratio, and then in this case here, I use 6, K equal to 6, right? So, and the rest, I don't want to store the data, I just want to calculate it, right? That's what you get. right? And then this is what the number you're going to see in the next slide. This is what the chart looks like, right? And I can show you, if you want to do the ANOVA method, you can also do that, right? This one will give you almost the same thing, but then, see, in your calculations, you include the part and operator interaction. So you give a little more resolutions, inside there, that sort of things there, right? Okay, so but nothing to worry about. Exam, I won't give you, it will be a little bit more, XRR, the one, the familiar things. How much you can calculate, right? Okay. So in the Minitab, what you're going to see is that I just introduced it. It's not just that highlight to you there. See? The Minitab is very smart. They give you all kind of equations. Subsequently, you choose whichever part you want to interpret, and they don't want you to give the argument of. They give all equations. You say, hey, this is not these are things. Then they give you all the equations, and then you go to interpret yourself, right? So this is what they do. This is an Excel. They give you all kinds of solutions, percentile, those are things there, right? That's what they do. And based on that calculation there, we have, right, our gauge R and R in this one, and then repeatability calculated this guy, right? Part to part, right? And then after that, we put the square root of this thing. This is what it is. So, but we know that this part and this part add together cannot give you this part. It's only the square. So they give you a variance comparison. This part of it, this portion of it, is all variance, right? That means it's this term, right? So this one square is this term, this guy square is this term, this one square is this term. So this term, you add together, you get this one, right? So this square of this guy here is this one. So this is term. And this part here is you add this and that. It's 10. Right? Right. And this percentage. So they give you this one divided by this one is 12%. Correct? 1.2 divided by about 10 as well, right? So this one here, this one here, and then you get 87%. So this guy here is add together, you get 100%. Because variance can add, right? So this is what it is. Now, so at least you look at it, the variance part contribute about 88%, and R and R is 12%, but inside there, the repeatability is a bigger problem than reproducibility. Right? So you want to go back and then calculate what we have, right? Based on the PD and the GRR. So Minitab also give you, since we have the sigma, this guy is all sigma, right? These are sigma squared, right? So in the table there, when I put inside there, in the Minitab, I put 6, I can put 5.15, then 5.55 and come out with this one, but in this case it's 6. So 6 times this one here, it will give you this column here, right? All this part here. And you see that you cannot add together to give you this one, huh? Okay? But anyway, you follow the tradition, right? So now, this is the GRR, right? So GRR is this one, 6 times SD, right? Over the total, right? This guy. So this is what it is. Right? 34%. Okay? Right, so subsequently this is what it is. Right? In this case here, you can see the element, but this guy add together is 120, so it's not 100%. Huh? Okay? So you cannot add. Huh? This one 100 because it's this one divided by itself. Right? It's 100, right? Okay? But you cannot add. But in this case here, you can add. This case here, you can add. This guy, you cannot add. So this is our PD. Right? So our PD is upper spec minus lower spec is 55, right? So 55 is our base, right? So this guy divided by 55, this is our thing, huh? So this is what it is, right? So I don't want to confuse you this one. In the trade, people use the class of distinction there. This is the equations that part to part divided by this guy times 1.4. So it's 3.2122 divided by 1.1169 times 1.41, and then equal to 3 point something number, and then Minitab truncate it and give you 3. So there's a lot of interpretation to that. Very debatable. But Minitab give you the number, so I don't want you to get. So to us, we stick to our slide there, 0.1, 0.3, 0.2 to 0.1 to 0.2 to 0.3, those are things there, right? That kind of stuff there, see? So to make our judgment on what is the recommendation to use the gauge or not to use the gauge. So in this case here, see, our gauge here, right? This is 0.3467, right? This is 0.12. So it's right. This is what close to what we have. Because now remember this is 5.15. We use 6, this one will be 12. 0.12. Right? If we use 6. So this is, and then the GR and R doesn't involve with the K factor. So this one is the same, right? So this is what it is. So, good. So this is calculation, is very mechanical then, right? Minitab, we give you this one, just show on that, For that, at least you know what it is, Minitab give you this X bar R chart, right? This guy that you see earlier, this one you see earlier, and then this one is that they give you also this thing here, appraiser and part number and appraiser interaction. That's what I said earlier, right? So in our thing here, we care, because they use some ANOVA there, is it? Okay? So in this case here, right, we important thing for us is that you look at it, the R chart, no funny thing, right? No out of control. Okay, all good. And then the X bar, you want it to be a lot out of control. That's good. And then they give you this mumbo jumbo. They just say, okay, if you use a different calculation, right? Part to part, this one contributions, this one due to the GRR, this one due PT ratio there, and say that, okay, you know, how if you calculate this part here, different by criteria, what does it look like? The main thing is that you want it to be this one as big as possible compared with this one, so that to show that your GRR is good. Right? Okay? So it's very mechanical. Once you know this thing here, right? The important thing is that know this table very well. This one is subgroup size. And in some slide I use N so that you all don't confuse with that. At least that this one I personally put it N so that you know it's sample size. But actually in the Duncan one they use M. And this is the number of subgroup or the number of sample. In your infinity number of samples there is a D2. The rest there, you see, you use the D2 star. Right? So once you know that, it's very simple. Very mechanical, plug in the equation, you know how to interpret it, that's good enough. Right? So, a little bit variation. Inside the AIAG handbook, this is based on 2002, the third edition. They want to show you fourth editions. Fourth edition, they added more. Originally it's 80 pages, go to 100 over pages, 100 pages, now it's 200 over pages, you know, those are things there. Every time we need to we cover more ground. So basically, it's about the same, right? They put in a little bit more fanciful football. But if you know our equation steps, follow the step good enough because you are all engineers. This one, they provide it because a lot of, in the shop floor area there, a lot of technicians, a lot of people have this, they call it, in US, all those are things there, our secondary school, all those people there, see, this guy, they say that, oh, so they don't know the principle, so we give it a template to do the job. So they give a template, right? Remember this EV, equipment variations, is our repeatability, right? Appraisal variations is our reproducibility. So what they do is that actually this is nonsense. Earlier they used 5.15. I think they still stick to 1.5, but they recommend to use 6 in the 2010 onwards, something like that. But then we know what it is, so as long as you specify what is the K value, people will understand. So they just give a template, they say they multiply it out, and then this guy, see, because you get this EV there, right, I and R, see, it's 5.5 times there. Because when you take square this, you take it out, it's 5.5 GR and R, right? This is what the number is, right? So part to part, you know what it is. Total, you know what it is there, right? So they give all this equation there, and then say this total variation, part to part variation there, and then they give the equation, this is what it is there. And then, they say, they give another variation, right? Percentage P, this equation, AB is this equation, GI and R, this equation. This one is a little bit. If you know what we covered in the earlier template, you know the step there, you can do it. But this one is just that they want to come up with this thing, and then subsequently they come up with this table template, right? So they say, oh, you get the number, you get A, B, C appraiser. Everybody have 2 trials, you have 10 parts, you get the value, so you calculate the average, 0.625, the range is 0.05, right? So this thing you fill in, so you take the average of this one here, oh, this is what it is. You take the average of this row here, this is what it is. Then the second appraiser, same thing, you get this one, you get this one. Third one, this one, right? Template, shop floor, right? So once you get that, they say, okay, you take the average of this guy here, you take this part, right? It's another value, A1, A2, A3, or something like that, right? Then you don't need to take the average of this one here. You can take the mean, but our purpose is to get the range here, right? To get the part, sigma part to part, right? Remember? So we want to get this one is the RP divided by D2 asterisk, depending on part, right? So they give you template this one, and then they calculate, oh, what is the double R bar there? It's based on this divided by number of appraisers. So we get this one, divide our appraiser, you get this R bar, right? So this one, and then you get the upper control, lower control limit. And subsequently, oh, plug in this equation, you get the repeatability. Plug in this equation, minus out this is estimated, right? And then minus out this one, you get the right thing. Get this one, you get the right thing. This is for those shop floor usage, right? So you see, using the X bar R from this template alone, you can see that shop floor people can use calculators to do it. You don't need computer. But then if you use ANOVA, because of all the summations, minus subtraction, square, those are things there, you have to use computer to do it. So if you know the principle, it's quite simple. The value is slight variation on it, but then ANOVA take care of the other factor there, right? So this one, I didn't show the result here in our tutorial question number 1, right? It's precisely this number. So we can do it together, right? So this is what it is, right? So last few slides, and then before we go something on that, right? Now, if you want to do, if you encounter a situation one-sided spec, we don't have tolerance, right? One-sided spec. So one-sided spec, normally what can you do? Right? So one-sided spec, can you do PT ratio? One-sided spec? Because remember, PT ratio is equal to what it is? K sigma R and R over upper spec limit minus lower spec limit, right? You don't have a spec tolerance on this one, so you cannot do it, right? So, but you can do the total, right? GRR, right? So, right? Or you can do the process capability study, right? Do that. And then if you have destructive test, right? So people normally do is that same batch, they assume same batch is quite homogeneous. So the parts are all the same. So if I take one, destroy already, I say take part from the other guy there, it's also the same thing, so I'm okay. Right? So people can do these kind of things there, but in the Minitab, more elegant way is that you have another way to do it is using the nested tool to something there. I'm not going to bother with that. Once you know how the GR and R calculations there, in line of work, you need it, you can do something about that. So we are more simplistic in that sense, right? Okay? Then, how do you do reproducibility for that? You can have different operator to do the job as well, right? Same thing if you're a destructive part, right? So the gist of this thing here is that if we got a process, this is plot of X, okay? We got plot of X, and if your equipment, you measure, because your equipment has this sigma I and R, right? So you got a spread. Every reading you get it has a variation of that. And suppose that this is your spec. So when you measure a reading, this is your observed, right? Reading of those things there, see? And that your observed reading can be have this kind of range there. So sometimes the part is no good, Your unit is good, but then because of measurement error there, see, you may call this part is good. Right? You may reject this one. So in this case here, see, the part is bad, you may accept this one. So there's an error there, see? Right? So, and then to give you a bigger idea of what it is there, right? I plot the subsequent glass. This one you can also find AIAG in the appendix there, right? AIAG appendix. So, let's say that when you use the equipment, we have a certain variation inside there. So, whatever you use the equipment to measure, you observe a CP, right? You observe a CP. But if the true value of a CP is your actual CP, right? So our actual CP is this thing here, you know exactly what is sigma is there, right? Your observed CP is what you observe after you measure. So this is what our definition is. Use your equipment to measure, this is what it is. That's what you observe all the time. So the actual CP is equal to this equation. Upper spec minus lower spec over the process itself, right? And then we just expound on this one. The process itself, we assume that it's equal to product, those are things there, right? It's sigma square minus GI and R here, right? Remember this equation, right? Total equal to sigma square product or process plus sigma R and R, right? Square, right? So you just expand on this one, right? So then you take this guy outside the square root, 6, you take out there, right? So this one becoming divided by this one here, right? So you have this term, you have this term here, right? So this term is your observed value, right? And this is our term here, right? So what you do is that this is the observed value, this is the actual, right? So it's like y equal to m something factor there, right? X or something like that, right? We have this equation. So y is your actual, right? X, this is your x, huh? So you have a factor there, right? So this is an x. Right? So I just use this grid, substituting, this is our x independent, x value. Right? This is a response. So we plot this, we have this curve. And then this value here represents the so-called our CP value. Huh? CP 80%, 90%, this what is there. Right? So the actual process. So let's take an example. Huh? If we have a very good grid, a very good equipment there, right? Okay, it's 0.1. Right? When you observe this value here, you have a good equipment. The first line here, right, is corresponding to here. So you have a resolution of 0.1, right? In this case here, this is very close. I take another example here, extreme. If this guy is 0.9, so you observe CP processes you calculated based on equipment there, see, is 1, right? But actual there, see, is 2.3. What does it mean to you? You got corn, you are using a bad equipment and you have a lot of force reject. Because a lot of parts there are actually very good. CPs, actual CP is 2.3. 2.3 is better than 6 sigma, right? But then you see, because you use a bad equipment, your bad equipment, you give you the observed value of CP is really 1. Right? So this graph shows you that the impact of having a bad equipment and falsify your actual performance. Right? So this one is another graph, right? It's just based on PT1. This one I rather not for that. This one is exponential, go all the way to infinity, something like that. This curve on that. So it's just some interpretation, same thing derivations on this one here, see? And it's based on the PT that you have, right? So it's just same interpretation. Observe, and then your bad equipment, basically, you hide, camouflage actual performance. Right? Okay? So I'll finish this part to show you, right? So we have covered how are you going to do measurements equipment with GI. And then PT ratio and GI&R, in what application which is good, which is bad, right? Okay? Now, let's put together the following example. I show you 2 examples. One is for the service industry kind of example. One is for industry kind of example. Right? I just want to walk through with you when you say that, okay, we know the statistics, we know how the data central tendency, the standard deviations, or sample standard deviations, those things looks like, and then our control chart, process control, those are things there, how in actual case can be applied, right? Just quick walkthrough, right? Okay? SPC, statistical process control application. So this example we have a manager of a restaurant. We want to improve the service time, right? Response time. We say equality, right? You go to restaurants there for service industry, responsiveness is one of the important factor, right? So you have a couple of waiters, right, to attend walk-in customer. So his initial expectation is 2 minutes, the spec, plus 0 minus 1. So that means the upper spec is 2 minutes, lower spec is 1 minute. So we say that people walk in, you must respond, but sometimes 0 minute, you don't respond right away, right? Okay, so he have 5 waiters, and then take this thing over a few days. So with the 1, 2, 3, 4, 5, then we use a normal control chart thing there, right? To this range here. And then you take it over several days, right? So it's about 20 samples, right? So how are we doing? Right? So you look at this data there, how are we doing? So basically, we want to say, okay, what's the process capability, what is the standard deviations, what is the average, or those are things there, right? So this is, can they meet the spec performance or not? Right? Data is normally distributed or not? So you can plot this one in normally distributed. It's a bit, you plot histogram, you won't see it, but then normality there is a bit stretched and say that, okay, roughly normal. If you plot this average there, it will be normal. Okay? Right? You plot all the EG value, those are things that about there. So if you do that, right, and then you can get the mean, right? This guy here, and this guy, you can know what it is there, right? So we have 20 sample subgroup. What is the N? 5, right? So we can do all this stuff, right? So N equal to 5 there, you know, we can read out the right value there. We can go the range there, this sigma here, right? Estimated, I should use arrow here, right? So since we have this spec here, we can calculate CP and this guy here, right? We can do the histogram of the average, this is what it is. And then you can plot the control chart. So this one is all in control, right, based on the spec. So, but if you are the boss, are you happy? So the average wait time is 2.45 minutes. So if your spec is at 2 minutes, upper limit. So it's no good, right? Even though it's in control with the natural variation, it's controlled there, it's no good. So what I do is that, so you say that it's no good. So you say that set an alarm system. When a customer walk in, straight away, you see, he got the reader, right? A line up here, 1, 2, 3, 4, 5, right? So first customer response, second, you know, those are things. So right away, right, they do that, right? And then new data collected. So we collect this one here, collect this one here. We go through the same thing, right? And then you plot. The mean now is 0.8, right? This guy here, right? And this one here, and then the range here is here, right? And then you got the distribution here, sigma, all this, you know how to do it, right? So look at the graph here. Range chart is okay, but R chart is bad. You have a problems? So what is your thinking process? If you look at this one, straight away you say that from 2.45, my mean from 2.45 minutes reduced to this one. Wow, good performance. And my sigma is so small, right? CP is 6 sigma performance, you know. But this one is offset, so it's only 0.7 there, you see. So, but I got a lot of potential, you know. So, but then you look at the graph here, what happened? That means that over time, the people are getting used to it and then getting tuned to it and then very good. Correct? So over time, and then say that, okay, people say, how come we keep reducing there? See, now it's below this thing here, see? So that what it means is that your control chart, you have process improvement. Right? Improvement to the extent that it's so good, you can retune. And then you can replot, establish a new control chart. Right? Okay? Now, good, So another one. This is technical. Right? Just walk through there. The other one there, bonus, I'll do it next week. Spin coating. Who are in the wafer business? Anybody? Yeah, some of you are in the wafer business, right? Who is in Global Foundry, UMC, or TSMC, the branch here, or some guy, from this Reynosa or something, those guys here. Some of you are wafer one, right? Anyway, I look at it. This data is a bit on the most side of this stuff, but I mean just show some flavor, huh? So a wafer set up, trying to do the spin coating for photoresist process. Huh? The photoresist, if you do the mechanical, you do down, you spin and then spray it out. After that, you bake it, harden it, right? Then you go to a masking machine there, just you do exposure, right? So those that you want to get rid of, after you expose to UV light or something there, those exposed ones, get hardened or something like that. Those that not exposed ones, have different chemical behavior. After that, you go to etch. Etch out, so then you get the crystals or something there, right? But then etching, chemical duration or something there, and baking, all these are process variable control, right? But anyway, what is interesting is that when you do the photoresist spin coating there, you want to spread it out such that the coating are uniform, right? So they have this equipment provider, they always have some spin speed, and then subsequently they calibrate and say what is the speed, right? And then subsequently what is the thickness of the photoresist after spreading out, stabilize it, you see what it is there before I go to bake, right? So this is what their result, right? So some guy, a vendor, right, have the new machines, right? And that, so evaluating a new spin coater from a vendor for improving the process capability can improve, right? They want a CPK of 2, the intention, right, ready for new product. Before the evaluation, the vendor would like to make sure that the interferometer they use to measure, right, the photoresist thickness one, right, measurements there have a PT ratio of better than this one. That's what you want to achieve, right? The equipment is fully automated, so you want to do it, right? You go to a machine there, this interferometer there is a machine there, it does a laser, right? And then we get the measurements reading out, digital reading out, right? Or print out, something like that, right? So there's no reproducibility problem because operator just the guy measure it, right? So it's only repeatability, right? So the requirement is this thing, the spec, right? Plus minus 1,800 microns, right? So you want to measure the new equipment for vendor always say that, hey, your interferometer, is it good enough or not to measure my things there, resolution good enough before I do the evaluation? Your interferometer cannot have a good enough resolution there, then you screw up my equipment, you give a false reading, right? Just like we said earlier, right? So the guy said, okay, so in order to control the variability to a lot there, he said, okay, one batch of wafer so that the consistency of wafer is very good. And also then he said one bottle of photoresist so that all the variability control. Then they do 12 wafer, right, from that batch, and then measure 3 points on this side there, see? So in this case here, what they have is that we got this average value, 3-point average, right? And this is the Armstrong meaning here, right? So in this case here, we can do our bar chart, X bar chart, those are things there to do it, right? We don't have producibility problems, those are things there. So we can do it. So we can plot this one here, a range chart, and then this guy is here. So you can calculate out the R, right? It's 100, D2, all of this. You can get it from the sample, right? The sample size, right? You get it 59. But PT ratio then, the spec, you have the spec, so you come to this guy here. Okay, right? So, I simply, this simplified, okay, just to show that you say, hey, now I assess the equipment PT ratio is good enough, right? For this evaluation, everybody happy, right? Now you go to evaluate this thing here, okay? Actual process, they just have a CPK or not, right? So what they do is that, right, they agree, you use the tool there, and then they, they do it day and night, process there, right, for 5 days, right? Subgroup for each shift, 3 subgroups, right? The beginning, middle, and night time, or at the end of the shift there, right? So they, right, shift, right? Okay, so you sample this thing here, right? Okay, so they do it, and then they got 30 sample, 30 subgroup, right? And each of them, the n is 3, right? 3 measurement, something that you can average this thing here. So again, you go through the control chart, you go through the same thing, you calculate it, right? Get this one, right? Okay, this thing, normality, those are things there, right? Subsequently, there is it all. Okay. We all tired already, So, okay or not? Huh? So, based on the requirement on the first one, right? They want to have a CBK of 2, right? So, in this case here, right? CBK of this guy here, CBL, right? So, you buy the equipment? Huh? No one. You can achieve your processor. Right? Okay? So you can repair, right? People give you here and say, hey, this is a basic, you agree on the term conditions, we use it, okay, right? So these are the blah, 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 right? SBC, these are the steps you want to do. And then, these are bonus. I don't want to talk about it. We'll talk about next week, right? So we get a good feel for what we have so far. Data, you know how to do it, you know how to calculate, draw the histogram, those are things, normality plot, you know how to do control chart, you know capability, you know how to do the measurement. So basically, you can do your job already, right? So the last part will not be more, I won't give you for exams, and then it's good to know. It's for every time the management say you want to do a process, a lot of times there our process screening of part depends a lot on operator. Correct? It depends on operator, and then operator say that it's good, bad, reject, acceptance, sampling, those are things there, right? And then when your customer escape to the customer there, the customer say, hey, what did you say? Oh, operator fault. You blame to the operator guy. So, and then how do you know that how good is your inspection technique? How do you, can you mechanically certify the operator? Or you say that, hey, my way of certifying the process, there's something inconsistency there, it's good or bad. So I just give you some attribute, GR and R. So this one, I'll not touch it, this is a flavor. Just good to know, at least that you know such something will work. So I'll cover it very fast next week. Okay? So thank you very much. Thank you.